All right. So, um, welcome back. Remember yesterday, I had started to build the kernel, but then we were like stuck for a while before it just started going again. The build actually ended up finishing, but it was kind of slow. I didn't know why, but now I do. So, apparently it had to do with my the operating system I was using for the NFS. So the original thing that we downloaded was TrueNAS Scale, which is like the new version of whatever TrueNAS is. That's like the thing that kind of supersedes the old version of TrueNAS. And TrueNAS Scale is a little different in that I feel like it's like it's Debian based, and there's probably some things around it that makes it less optimized, maybe. I decided to go back to the old version of TrueNAS Core, and that's based off of FreeBSD. Interestingly enough, TrueNAS Core is much faster out of the box than TrueNAS Scale. I have no idea why. I I, I don't really care to figure out either. So in the video description, I'm actually going to point everyone here to where you can download TrueNAS Core, and so you can actually get the same effects in terms of working with the kernel through an NFS share and not having it be excruciatingly slow. So yeah, I just set up another VM again. I called it NFS2 this time, and I basically going back to. Let me just see if I can let me see if I can just full screen this. Like going back to my VM where I have mounted it, I have it the same way as I did just yesterday. It's just now pointing at a different IP, which is the FreeBSD version of TrueNAS. So, all that being said, I can actually build at a decent speed now, and I'll just like kind of demo that. Um, so I can just do make clean just to kind of get rid of everything um, that I have. It just cleans all the built stuff, so that's fine. Um, and then you'll actually see like the CPU actually is going to start being not really saturated, but you'll start to see some activity coming along. So we've already um, went through configuring the kernel before we built, but I'm just gonna quickly just do random like enabling and disabling of stuff just to kind of refresh everybody's memory in case that they're just like starting to watch this video and didn't really catch the end. So I have a clean uh, like folder now. Do keep in mind I don't think make clean actually deletes the config file. It's still here, but we can just reuse it. So I do make menu config, and then it's gonna bring up the menu again. So yeah, so I'll just kind of go and disable a few things just for fun. Let's see, networking device support. Mm, let's see. Actually, I don't. Oops, what's going on? Oh, because I'm full screen. Okay. I'll exit. I'll just disable ISDN, disable telephony, uh, disable, I don't know. Say disable those video driver. Oh, Macintosh device drivers. I don't need that. Let's see. Looks like that's about it that I can do real quick. Once you get into this, it's like you really want to just like disable more and more and more because it's like you want to get like a faster kernel. So yeah, I'll just disable NVIDIA Riva. I just won't care about the Radeon stuff. Uh, I'll keep these generic ones. I don't know I don't know what platform the VM is using. But yeah, just stuff like this per media. These are all modules anyway, so I don't really think it really matters too much. It just won't be loaded. Okay, good enough. So let's say I've already like configured my kernel to what I want to build. So I'm gonna just exit and I'm just gonna exit here. Do you wish to save? Yes, I do. Okay, so now I have my config written and I just do make. Now I'm gonna do -J, so multi-threading. I have 12 virtual cores here, so I'm just saying, oh, why not just do 24? So if I were to just start this, it should now work much faster than before. You can already start to see that right here. And then you'll see like the CPUs are actually now being saturated a little bit. So that's a good thing. Yeah. So we're in a much better shape now because the last thing I would want to have is like we stall at random moments and that affects our ability to iterate with code changes. But I think I'm pretty satisfied at this pace. This is like what I'm used to seeing, so that's okay. So yeah, let's just let this build in the background. It only takes a few minutes since we have a lot of CPU cores to spare and we're doing 24 jobs anyway. Um, let's just go back to reading. So yeah, so last where we left off is the book was going over like caveats about kernel programming, how much more it is like different than regular user space programming. So we'll just kind of continue. We last left off with static functions. So inline static is preferred if it's like a small function that can run quickly. You kind of want to prefer that, and you have to define it in the header. But if it's going to be an inline function that is long running, that's discouraged. So onwards. So inline assembly. Oh, by the way, my for some reason my tablet works today. I don't know why. Okay, so the GCC compiler enables the embedding of assembly instructions in otherwise normal C functions. This feature, of course, is used only in parts of the kernel that are unique to a given system architecture. The ASM compiler directive is used to inline assembly code. For example, this inline assembly directive executes the x86 processor's RDTSC instruction. Okay, so this one right here. Okay, which returns the value of the timestamp TSC register. So basically, if you wanted to inline assembly, you would kind of just like write your assembly code this way. Okay, meaning that you want to write assembly in C. The Linux kernel is written in a mixture of C and assembly, with assembly relegated to low-level architecture and fast-path code. The vast majority of kernel code is programmed in straight C. Okay, so that's a good sign because I don't really know much assembly. Branch annotation. The GCC compiler has a built-in directive that optimizes conditional branches as either very likely taken or very unlikely taken. The compiler uses the directive to appropriately optimize the branch. Well, that's interesting. I don't know about this. The kernel wraps the directive in easy-to-use macros, likely and unlikely. Huh. For example, consider an if statement such as the following. If error, do something. To mark this branch as very unlikely taken, that is likely not taken. Oh, so like the chances of this actually being hit and run, like basically occurring. Is my video choppy? Oh man, it's doing that so often. Okay. Um, okay. So basically, we want to mark this one as unlikely to be taken, so that we can just wrap this as unlikely error. So the boolean that comes off from this. So we predict error is nearly always zero. Okay. Conversely, to mark a branch as very likely taken, we predict success is nearly always non-zero, so likely. So it's most of the time it's always going to be successful. You should only use these directives when the branch direction is overwhelmingly known a priori when you want to optimize a specific case at the cost of the other case. This is an important point. These directives result in a performance boost when the branch is correctly marked, but performance loss when the branch is mismarked. So if you get it wrong, if it turns out that, well, you thought something was unlikely, but then it turns out to be actually more like likely, then you're going to lose performance. A common usage as shown in these examples for unlikely and likely is error conditions. As you might expect, unlikely finds much more use in the kernel because if statements indicate a special case. Okay, what else is different about the kernel compared to user space programming? Well, we have no memory protection. When a user space application attempts an illegal memory access, the kernel can trap the error sending the SIG-7V signal and kill the process. So this is user space. If you're accessing invalid memory, you will segfault. And kill the process, right? The process is killed. So normal stuff. However, if you're in kernel space, if you're running kernel program, if the kernel attempts an illegal memory access, however, the results are less controlled. After all, who's going to look after the kernel? Yeah, because it's usually the kernel that kills the user space program if the user space program is trying to access invalid memory. But then if you're the kernel and you're accessing invalid memory, who's gonna kill you, right? Who's gonna get rid of you and say, hey, you weren't supposed to do that? Memory violations in the kernel result in an oops, which is a major kernel error. It should go without saying that you must not illegally access memory, such as dereferencing a null pointer. But within the kernel, the stakes are much higher. Additionally, kernel memory is not pageable. Therefore, every byte of memory you consume is one less byte of available physical memory. Oh, yeah, okay. So there's no paging in kernel memory. So if you are going to consume memory in the kernel, you're taking that away from physical memory. And so the address space, although in user space, still stays the same because it's virtual. The amount of physical memory you truly have available is reduced because the kernel is taking up more stuff. So keep that in mind the next time you need to add one more feature to the kernel. Okay, and here's the one that I'm like really like kind of scratching my head about is like the use of floating point. I'm not sure why this is such a big deal. So let's see. No easy use of floating point. When a user space process uses floating point instructions, so they're talking about floating point instructions. The kernel manages the transition from integer to floating point mode. What the kernel has to do when using floating point instructions varies by architecture, but the kernel normally catches a trap and then initiates the transition from integer to floating point mode. Oh, so there's two modes of execution when doing things. There's a separate integer and floating point mode, and I guess like it's so dependent on the CPU architecture that's actually not as easy as it seems. Okay. Unlike user space, the kernel does not have the luxury of seamless support for floating point because it cannot easily trap itself. Using a floating point inside the kernel requires manually saving and restoring the floating point registers, among other possible chores. Yeah, because floating point computation is done in a floating point unit in the CPU, so it's like a completely different place. The short answer is don't do it, except in the rare cases. No floating point operations are in the kernel. No floating point operations are in the kernel. Wow, there's like no floating point operations at all in the kernel, huh? That's interesting. That's millions and millions of lines of code, and you never have a floating point operation. That's amazing. Okay, so the kernel also has a small fixed size stack. All right, so user space can get away with statically allocating many variables on the stack, including huge structures and 1,000-element arrays. So that's user space. You can like do a lot of things with stack memory. Probably use more than what you really should. This behavior is legal because user space has a large stack that can dynamically grow. Developers on older, less advanced operating systems, say DOS, might recall a time when even user space had a fixed size stack. Okay, so the kernel stack is neither large nor dynamic. It is small and fixed in size. The exact size of the kernel stack varies by architecture. On x86, the stack size is configurable at compile time and can be either 4 kilobytes or 8 kilobytes. Historically, the kernel stack is 2 pages, okay, which generally implies that it is 8 kilobytes. So one page is 4 kilobytes on a 32-bit machine. So this is 8 kilobytes on 32-bit architectures if it's 2 pages. And then since a page on 64-bit machines are 8 kilobytes for 2 pages, it's going to be 16 kilobytes on 64-bit architecture. The size is fixed and absolute. Each process receives its own stack. The kernel stack is discussed in much greater detail in later chapters. That's fine. Okay, so synchronization and concurrency. The kernel is susceptible to race conditions. Unlike a single-threaded user space application, a number of properties of the kernel allow for concurrent access of shared resources and thus require synchronization to prevent races. Specifically, first, Linux is a preemptive, meaning that it's the OS that kind of schedules processes. Processes don't actually let go of execution. It's, they have no choice but to let go. So Linux is a preemptive multitasking operating system. Processes are scheduled and rescheduled at the whim of the kernel's process scheduler. The kernel must synchronize between these tasks. Linux also supports symmetrical multiprocessing, or SMP. Therefore, without proper protection, kernel code executing simultaneously on 2 or more processors can concurrently access the same resource. Okay, we know that. Interrupts occur asynchronously with respect to the currently executing code. Therefore, without proper protection, an interrupt can occur in the midst of accessing a resource. So an interrupt can just happen at any time. And even like, for example, you're like writing to disk, interrupt can occur. Okay. And the interrupt handler can then access the same resource. So then the handler then could be writing to that file too. And so it's like you have to take care of that concurrency. The Linux kernel is preemptive. Therefore, without protection, kernel code can be preempted in favor of different code that then accesses the same resource. Okay. Typical solutions to race conditions include spin locks and semaphores. Later chapters provide a thorough discussion of synchronization and concurrency. Next, the importance of portability. Although user space applications do not have to aim for portability, Linux is a portable operating system and should remain one. This means that architecture-independent C code must correctly compile and run on a wide range of systems, and that architecture-dependent code must be properly segregated in system-specific directories in the kernel source tree. So we need to program the kernel in such a way where we can make various forms of it for different CPU architectures. A handful of rules such as remain Indian neutral, meaning that the byte order, how you read the byte order, you shouldn't be like so dependent in writing code that depends on reading like the high byte first, low byte second, low byte first, high byte second, things like that as you are like interpreting instructions. Be 64-bit clean. Do not assume the word or page size, and so on. So they all go a long way. Portability is discussed in depth at a later chapter. That's good. So that's what it means for the kernel to be portable. You shouldn't be programming in a way where you depend so much on the details of your CPU architecture in this case. Conclusion. To be sure, the kernel has unique qualities. It enforces its own rules, and the stakes managing the entire system as the kernel does are certainly higher. That said, the Linux kernel's complexity and barrier to entry is not qualitatively different from any other large software project. Oh, we'll see about that. The most important step on the road to Linux development is the realization that the kernel is not something to fear. Unfamiliar? Sure. Insurmountable? Not at all. I love this guy's encouragement. It makes me feel good that we can do this. This and the previous chapter lay the foundation for the topics we covered through this book's remaining chapters. In each subsequent chapter, we cover a specific kernel concept or subsystem. Along the way, it is imperative that you read and modify the kernel source. Only through actually reading and experimenting with the code can you ever understand it. The source is freely available. Use it! Cool. Okay, so before we move on to the next chapter, let's check up how our build is doing. Still going, but it looks like it didn't even slow down at all, so that's good. Wonder how much we have left. Let me just shrink that a little bit. Looks like it's not that bad. Looks like it's, see, it's at the driver's media, driver's net. Okay. So what I want to do after compiling it is to do the rest of the steps, like make modules install, uh, and then also make install, and then see if we can actually boot to this new kernel that we built. So just to like remember, it's 2.6.34. So yeah, okay, looks good. Well, I guess we can just continue on while we're waiting. And so let's hop right on to it. Okay, process management. This chapter introduces the concept of a process. Oh, what the heck happened? Concept of a process, one of the fundamental abstractions in the Unix operating systems. It defines the process as well as related concepts such as threads, and then discusses how the Linux kernel manages each process, how they are enumerated within the kernel, and how they are created and how they ultimately die. Because running user applications is the reason we have operating systems. The process management is a crucial part of any operating system kernel, including Linux. Okay, so what is a process? A process is a program, object code stored on some media in the midst of execution. Processes are, however, more than just executing program code, often called text section in Unix. Okay, they also include a set of resources such as open files, pending signals, internal kernel data, processor state, a memory address space with one or more memory mappings, one or more threads of execution, and a data section containing global variables. Processes, in effect, are the living result of running program code. So a process, you can think of it as like a data structure. Okay, like a data structure that includes, I guess, like many things, like the running code. Okay, like text, basically the compiled code that gets loaded. References to some memory address space so that your program can actually operate and do memory operations. Um, Files, open file handles. Remember, we had like the std in, std out, std error, which were like 0, 1, 2, right? You can have files, which is like 3, 4, 5, 6, and so on. You have signals, and then you have uh, registers and like stack, things like that. That represents like an entire execution context of your program that you're running. So your program itself, when you built the program, right? When you built the like a dot out, that's actually just binary. So like kind of looks like this in a sense. Like, so like let's just take your program for example. Prog.c. Actually, no, not prog.c. Let's do a dot out. Okay, so you have like a dot out here, and that's like a lot of instructions. This is 0, 1, 0, 1, 1, 1, 0, 1, and so on. Okay, so this, like your program here in your disk, is what we consider like text, right? Program text. Now, when you load up the program into like a process, for example, like just think of this as like a container process. Okay, you get many things. Like you actually get this as like the program text. You got out. Just visualize it. It's not accurate, but just like oversimplify. You also get like registers, CPU registers, like a mirror of the registers. You also get things like maybe a stack. You get files. You also get like You'll have things like a PID, like the process ID. You also have like other stuff like global variables, and so on. So like this this program is just one small part of what a process is. And remember, like the process is like a running context, right? For it has everything you need to uh like it has everything available for an operating system to kind of just manipulate it, run it, and store data and state, right? Regarding that instance of a process. So that's the reason why it's like literally you can create. That's the reason why you can start multiple versions of your program. They just have different states in this case. So like you take a look at this one here, this process, right? This is process B now maybe, and then this one is like process A, and they are both running A dot out, right? They are both running A dot out. They're the same. They're running the same program, but they will have different variable states, and everything about it. It's like the same thing as running multiple like Firefox tabs or multiple VS Code windows and so on. Let me try to make this smaller. Maybe 80%. Yeah, something like that. Yeah, well, maybe one more. Is that okay? That looks okay. Yeah. Okay. So looks like we're still going. Okay, we're still going. It's compiling a bunch of drivers. Okay. So so basically, you need this type of structure because the kernel needs to manage all these details effective or efficiently and transparently. Okay, so threads of execution, often shortened to threads, are the objects of activity within the process. Each thread includes a unique program counter, a process stack, and a set of processor registers, just like what we just mentioned. The kernel schedules individual threads, not processes. Okay, so like let's back up a little, right? So remember how I drew this and I said process A, process B, and so on? Well, in Linux, right? In Linux, actually everything is not really a process per se. It's actually closer to a thread. It's not really a process, it's a thread. And here's the way like I kind of imagine it, right? So like in a traditional system, whoops. In a traditional system, why is this? In a traditional system, like Unix, for example, you have a process, but then you'll have basically a list of threads, right? And then you also have like a PID, and then you have so on. But in Linux, everything is kind of like a thread itself, and that has like a PID, all that other stuff. So Linux is different, okay? Like process contains like a bunch of threads because like they want to share the same memory address space. Whereas it's like in Linux, everything's kind of like it's still like a process itself, but then we don't refer to them as like a process. We refer to them as threads. Even crazier, so they're actually not really called threads; they're called tasks in this case. Okay, so that's like a preview of like terminology. So like if let's say you spawned like let's say you had like a Chrome process, right? And you have like 5 tabs. That's like 5 Chrome processes. They're technically not 5 Chrome processes. They're all on 5 Chrome threads on Linux. There's like not one like master process that's containing all these threads or anything like that. So yeah, in traditional Unix systems, each process consists of one thread. Okay. In modern systems, however, multi-threaded programs, those that consist of more than one thread are common. As you will see later, Linux has a unique implementation of threads. It does not differentiate between threads and processes. To Linux, a thread is just a special kind of process. On modern operating systems, processes provide 2 virtualizations, a virtualized processor and virtualized memory. So basically, every process kind of thinks that it's the only one executing in a system. So it's like it thinks that it has all the CPU. It thinks that it has all of the memory. So what ends up happening is that you're technically running your process in like a virtualized context, right? So in this case, it makes sense that your process in this case, I keep using process, but yeah, it's basically like a Linux task, a Linux thread, whatever. Okay, it has its own state of CPU registers, and it has its own like memory address space. That information is within like that structure. Okay, and so what ends up happening is that whenever you switch processes, you basically kind of save those state of those registers, and then like load up the next processes registers really on the CPU, on the physical CPU. And then when it's time to switch again, you take those physical registers out of CPU, you save it back into like your that currently running processes context, and then you move on to the next process, and you load the previously saved registers back onto the CPU, and then like memory and all that stuff is all like updated correctly to switched out, and we call that like a context switch. So like whenever you do things like this, for example, like you're literally context switching, right? So pretend those are like different programs. So yeah, it's not like a virtual machine, but it's just like a virtual execution context. Like all processes always think that, at least processes in like the user space, always think that they're like the only one in the system, and they have like no idea that there's another process waiting to be run, and the kernel handles like switching back and forth between state of your computer to accommodate the state of the world, to like recreate the state of the world for that currently running process. And then when it comes time to run the next process in the queue, for example, your the kernel is gonna kind of blow away that state of the world safely, save that in, and then redo the state of the world in context to the current running process. So you need a way to kind of model all this. Like you need a way to model the CPU, and you need a way to model the memory, so that you create virtual versions of them. Processes operate in this virtual version, and then the kernel handles like all the real stuff, updating the CPU that way. So yeah. So the virtual processor gives the process the illusion that it alone monopolizes the system, despite possibly sharing the processor among hundreds of other processes. See Chapter 4, Process Scheduling. Or Chapter 4, Process Scheduling, discusses this virtualization. Virtual memory lets the process allocate and manage memory as if it alone owned all the memory in the system. Okay, so virtual memory is also covered in Chapter 12, Memory Management. All right. Okay, let's see where we are at. Okay, we're done. Look, cool. So we are done with building the kernel. If we did LSLA, we'll have, I think this thing here, like a binary. I think it's how many bytes is that? It's like 117 megabytes, maybe. Yeah. I think that's just the kernel image right there. We're not done yet. We had to install the modules that we built. So we just do sudo make modules install, I think. And that should pretty much load all the modules. Okay. Yeah, there we go. So it's installing all the modules. So we're literally installing the kernel that we just built into our system, into this VM. So I'm gonna just full screen this as if it was like a real computer. Okay. So that's going to install. I need to check messages. Okay. So once that's done, we need to install the kernel itself. Again, sudo make install is the command. So we'll do sudo, whoops, sudo make install. So that'll basically do stuff to copy. I think copy the image somewhere to our boot partition. I think, and then what we want to do is then we want to actually update grub uh, so that we have like a nice menu to choose which kernel we want um, to use. Because by default, I think Ubuntu doesn't do that. It'll just like load up whatever kernel it finds. So we need to update some settings here. I'm trying to remember what that was. So we do sudo vim. I think it's maybe dev. No, maybe etc defaults. Let's see. Uh, grub, grub, grub d. No, not here. Let's just ls root, and then I can finally see. I think it's USR, maybe. Let's see. So ls usr grub, not usr lib, no, grub. Let's see. Yes, I can just look at it. Let's see. Yeah, you know what? Let's look for it. So let's go back, and then let's do Firefox. Update grub configuration Ubuntu 10. Where is it at? Oh, boot. No, let's regenerate. Oh, etc default grub. Okay, we need this. Okay, so this file is where we will actually update our settings, I think, to... No, this is for menu. Grub menu selection. Menu timeout. Let's do timeout. Etsy default grub. I guess it is Etsy default grub. Okay, so we can go to Etsy default grub. So vim Etsy default grub, and then I think we need to be sudo for this. Okay, there we go. This is what I want. Okay, so this is like the settings to actually handle all that menu selection so that Ubuntu just doesn't blindly go to whatever kernel. I think what we can do is we can say grub timeout. We can say that's -1. I think when we say -1, it will never ever move and proceed to booting until you explicitly choose a kernel you want. Hidden timeout, I forgot what that was, but I think I usually set that to 30. No quiet. I like logs and noisy, so I also remove quiet and splash here too. So this is what I usually. This is what I actually usually do when I. Why is this like that? What is going on? Oh, it's getting. Oh, it's. It's fine. I'm trying to go in normal mode for Vim, but then this thing is like being affected. Okay, so how do I do this? I just can go to normal mode here. Okay, so I'll write and I'll quit. So grub timeout -1, grub hidden timeout 30, grub hidden timeout quiet false, and then I remove the quiet splash on this. Let me see if I can just pop out this. Can I? Yes, I can. Okay, that didn't work. Shift 4. Okay, that just works for now. Okay, so now I've updated this. I'm not quite done yet. I've updated the grub configuration file. I've installed the kernel, but I need to update grub to actually make all the changes take into effect. So I do sudo update grub, and that's going to generate a new grub configuration file. And then you'll see that I found a new kernel that we just built, 2634. Whereas we're currently on 2632. So it found all these images and it's gonna like update its menu entries. And we can verify that we're actually running a 2632 right now. So that when we reboot right now, we should be able to see a selection where we can go to 2634. So if I do sudo reboot, for example, if all goes well, I should be able to select it. So, okay, that's great. So notice here now I get a menu. Let me see if I can zoom in a little bit. Can I zoom in? Yeah, I can do. Okay, so notice how I get like a menu. This is the grub menu. I can select whatever kernel I want here. Okay, I don't know why it doesn't work when I'm zoomed in this much. Okay, weird. Let's go back to this. Let's go back, pop that out again, send it to 4. Okay, so I'm gonna choose 2634 and let's see what happens. So now we shouldn't see any like splash screens or anything like that. We should see a bunch of logs spilling in at us. And this is like a good way to actually kind of just follow any logging that you actually will put into the kernel. So uh, yeah, a lot of it looks scary, but I think as we get better, we can actually learn. Okay, so yeah, so this is by default 1080p, so that's fine. We change our resolution back to 1024 by 768. Okay, cool. So it looks like we booted correctly. Let's verify that we actually have the right kernel version. So we do rename -r again. We should see that now we're running 2.6.34 kernel. This is the kernel that we built together. So pretty good, pretty good. Yeah. So then you can do certain things, right? Like um, for example, you can add to verify that you're indeed running your changes. Once we dive into code, we can start writing print case statements so that we can actually see if what we're doing is correct and that we're actually truly running a kernel. We look at our logs using dmesg, so dmesg. All the print case stuff kind of gets dumped in here. So then you can actually see your work being done. So yeah, that's like a preview. This is like the model that we'll be working with. Like we're going to um, always edit our code in our tree here. Okay, we'll edit our code here, and then we just do make j blah blah, and after that we do make modules or sudo make modules install. Okay, and then we do sudo make install. And since we have already kind of tweaked our grub settings, all we have to do is do sudo update grub to pick up the new kernel image and add that to the menu entry, and then just reboot, and then you should be able to see it. And if you ever mess up, for example, if you remember, if you ever mess up something and your kernel can't boot anymore, the one that you built that is, you could always reboot your computer and you can actually always go back to your old kernel. And this is what I mean. This is what I mean by like being able to save your old kernel so that you can actually not be in a disastrous state. So yeah, so now we're like enabled now to freely make changes and mess up and not be able to be like we shouldn't be scared now that we have like a means to recover. So as long as we can get back to our old kernel, and let's say we didn't have that menu, we can actually always go back and edit the grub config file to kind of include those menu entries as long as we have the path to the kernel image. So yeah. Okay, so now we'll wait for this to load and we'll do a uname -r just to see, and then we'll see what happens. Okay, okay. So now we're in our 2632 kernel, most likely, and then we did uname -r, and we'll see that we are in the kernel that we chose to boot into. So that's good. But I want to enjoy the new kernel now, so I'm going to reboot again. And I'm going to boot into 2634 and we're working through there from now on. So yeah, I mean, building the kernel is not as hard as it may seem. It's just knowing to configure and then kind of edit your bootloader's configuration files to actually choose it is the trick, I say. So Yeah, it's definitely a straightforward process. And I think that's like a testament to like the code base, right? Like the make files and everything. It's just it's written so well. And this is like almost 15 years ago too. So um, I did uname dash r. There you go. So okay. Um, yeah. Okay. Let's see. Let's see. Okay. I kind of want to stop right here for today. I'm a little bit squeezed on time, but let's go deeper. My goal today was actually to get the kernel built and installed and just show you guys and start talking about processes a little. We'll dive deeper into that next time. And yeah, thank you. Uh, Felt like today was like redemption for me to show that I can indeed build a kernel. Thanks.